Good morning, Year 11s. Today we're going to look at similar shapes, so in 3 dimensions this time, and why giant spiders don't exist. We'll get to that in a second, and of course we're going to end with a cat video. Thanks, Annabelle. Now, here we have a cube that's been enlarged by a scale factor of 2, and you can tell that because this length is half of that one. So to increase the lengths, you simply multiply by 2. Now, that there is the ordinary scale factor. Or we can say the ratio of the lengths, there is a ratio of 1 to 2. Now, surface area we looked at last week, you can see there that it has increased by a factor of times 2 to the power of 2. So their surface area ratio is a factor of 1 to 4. Or to get the surface, you blow it up by a factor of 4. Now, volume. Count the volume of the first one. Clearly, it's a 1 centimeter cube, so the volume is just 1. If we double it, well then the volume becomes 8. Which means when we find the scale factor, it's the length scale factor, but to the power of 3. Because 2 to the power of 3 is 8. And the ratio of their volumes is 1 to the 8. Now, we can check to make sure this works with all shapes, or at least one other shape, by trying it with 3. Here, length scale factor, multiply by 3. 1 centimeter to 3 centimeters. Surface area is from 1 to 9, which is 3 squared. Volume, from 1, if we count them all, 27. Or 3 to the power of 3, which is 27. So, in general terms, if you've got a scale factor of 2, the length increases 2 times. The area increases 4 times, the volume 8. Scale factor of 4, the length increases 4 times, area 16, volume 64, etc. X squared, x to the power of 3. Now, what does this have to do with ants? And this question comes up in biology, and almost every year, well, certainly a lot last year, students were asking me, I don't get this for biology, how's the maths work? So, let's take an ant that's been enlarged by a factor of 3. So its length is 3 times as long. This width here, if you multiplied it by 3, you'd get that width there. And same with the height. If you take its height, multiply it by 3, you'll get that height. Alright? Now, let's just look about the small ant now. If we look at the small ant's strength and weight, and I've put a picture of me there with top off to give you an idea of what strength is. Its strength, let's say its strength is 1, and its weight is 1. We're saying it has the strength of 1 ant and the weight of 1 ant, which is good because it needs that 1 ant strength to lift the 1 ant weight. So it can do all ant stuff 1 ant to 1. After we've blown it up though, strength is proportional to cross-sectional area. So of the muscles. It's how far across the muscle is that gives you the strength. So when we scale it up, we use the area scale factor, which is 3 squared. So now, that's 9. So an ant that's been enlarged by a factor of 3 is 9 times as strong as it was before, which is pretty scary, right? Look at weight, though. Weight is proportional to volume. That's terrible volume. And E on the end. And what do we do with volume? Well, volume is 3 to the power of 3, which is 27. So its weight is 27 times as large as it was previously. So if we take an ant, blow it up by a factor of 3, it's quite a scary ant, because it's 9 times as strong. But we've got to remember that the ant is now 27 times as heavy. So its strength to weight ratio is terrible. It's a third of what it was before. And if we blew it up by 4 or 5 times, this ratio would keep dropping. Which is why ants can't keep growing bigger and bigger and bigger. They've got to stop at some point, otherwise they just get weaker. If they do want to get bigger, they've got to evolve and change shape, and after a point, they end up looking like elephants, which, okay, has ant in the name, but sorry, there's a spider on the screen, I've been talking about ants. You get the point. I could replace it with a picture of an ant, and the same logic would hold. Elephants look very different. They have much, much thicker limbs to support that weight. And even there, their weight to strength to weight ratio is much poorer. You hear spiders and ants being able to lift 3 or 4 times their weight. There's no way an elephant can do that. Its strength to weight ratio is nowhere near as good as an ant's because of that scaling up. Alright, so in your OneNote, I'd like you to use the volume scaling concept to work out the volume of this smaller container. You'll need to work out the scale factor. That's the length scale factor. Then divide by the length scale factor to the power of 3 to work out what that volume is. Now, as promised, one cat video. You just get 2 vines.
Okay, get out. Oh!
See the strength to weight ratio for the cat? It jumps amazingly. I couldn't do that. Alright. Thank you very much. I will see you next lesson.